Thanks for the introduction. It's great to be here. So when we try to construct models for some data sets or for some system because we want to make some predictions or because we want to support some kind of decision making, we typically encounter three major sources of difficulties. The first one is that real-world systems, as we all know, are typically very complex. There are many variables, many features that we have to take into account, and this naturally leads to some very high-dimensional spaces that we have to consider if we want to model all possible interactions between the variables. The second major challenge is that we typically only have limited information about the systems we're trying to model. There could be uncertain parameters, there could be noisy measurements, there could be some quantities that we don't get to observe. So if we want to build robust models, we often have to take a probabilistic view of the world, and we have to construct stochastic models. And finally, we're typically building these models because we have in mind some task that we want to solve. And so we also often have to consider some preference or some kind of utility function, and we have to optimize for that as well. Now, these three challenges are very important, and they have been studied for a long time, not only in computer science and AI and machine learning, but they also have come up in a variety of different fields, ranging from economics, various fields of engineering, statistics. They are central to operations research. They even come up in physics if you think about statistical physics models. So it's not surprising that there are entire subfields and subdisciplines that deal with one or more of them. Think about optimization, statistics, combinatorial reasoning. And my research is really lies in this intersection here, highlighted in red. I deal with probabilistic reasoning. How do we make inferences automatically about complex, high-dimensional statistical models? And decision making, where we have this extra level of complexity of having an objective function that we have to optimize for. For example, when we want to figure out what is the best way to interact with a system that we modeled probabilistically. And my research in this space is motivated by a number of applications, especially in this emerging field of computational sustainability. And computational sustainability is a new field where we're trying to apply computer science techniques and AI techniques to help solve some of the big sustainability challenges of our times. And I worked on a range of problems in this space, ranging on how to find policies to optimally manage natural resources over time, policies to optimize the use of batteries in electric vehicles, helping material scientists to automatically analyze large amounts of data and speed up the discovery of new fuel cell materials. I worked on distributed inference problems for habitat monitoring. More recently, I've been working with economists on building large spatiotemporal models to understand the distribution of wealth and livelihoods in developing countries. And unfortunately, today, I don't have much time to talk about the application side of the research. But instead, I thought I will tell you a little bit about some of the techniques that we've developed to deal with some of the research challenges that we encounter by working on these concrete real-world applications. So what do all these problems have in common? Well, we are building statistical models. What this means is that the quantities of interest are modeled as stochastic or random variables. And the models are really joint probability distributions that tells us how likely each state of the world, each scenario is according to the model. And given a model, the basic task that we want to solve is that of making inferences based on the model. For example, compute the probability that an object is in a certain location, given that we observe some measurements. Or in a decision-making problem, we might be interested in figuring out how well will a certain policy perform on average, given a probabilistic model of the world. And it turns out that if you want to learn models from data, if you have some data, you want to build a model, you want to fit it to the data, it turns out that probabilistic inference is also a key subroutine for many types of learning algorithms. So probabilistic inference, this problem of making inferences about complex statistical models, is really one of the cornerstones of statistical machine learning and statistical applications in general. Now, given the importance of the problem, it's not surprising that it has been studied for a long time. In fact, the earliest algorithms for probabilistic inference were developed back during the times of the Manhattan Project to study the diffusion behavior of nuclear particles. Since then, there has been a lot of progress with contributions from different fields, computer science, physics, statistics. But somewhat surprisingly, to date, there are only a a couple of main approaches to solve this problem. The first one is Markov chain Monte Carlo algorithms, where the idea is that if you want to make inferences about some complex statistical model, what you can do is you can set up a Markov chain that in the limit, if you simulate the chain for long enough time, it will converge to the target distribution that you want to study. Then by simulating the chain, you can get some samples, and using the samples, you can estimate statistics of interest by taking, say, sample averages. The challenge of the Markov chain Monte Carlo approach is that we're only guaranteed to converge to the target distribution in the limit, and in general, it might take an exponentially large number of steps for the chain to actually converge to the target distribution. Variational methods are also very popular. They come from statistical physics. Here, the idea is that if you have a complex probability distribution and it's intractable, what you can do is you can try to approximate it using a family of simpler tractable distributions. Again, this tends to work reasonably well in practice. The challenge is that you typically have no guarantee on how well you can approximate, how well your approximation is going to be. So the work I'm going to describe today is a fundamentally different approach to solve this probabilistic inference problem that is inspired by ideas coming from theoretical computer science, such as universal hashing and combinatorial optimization. Some of these ideas were also developed also here at Berkeley and by other people. And it really nicely complements these previous approaches because it provides some strong accuracy guarantees on the qualities of the results that we get, something that Markov chain Monte Carlo methods and variational techniques typically do not provide. So let's start with, since I'm a computer scientist, I like to look at the problems from a computational complexity point of view. This is a widely believed hierarchy of complexity classes, going from easy to hard. We have P, we have NP, we have the polynomial hierarchy, and then we have the sharp P complexity class, which intuitively contains problems like counting the number of satisfying assignments from some constraint satisfaction problem. And it turns out that as you can expect, the problem of counting the number of satisfying assignments is believed to be harder than problems that are in MP, say like satisfiability testing, where you're simply trying to figure out whether there exists a satisfying assignment or not. And unfortunately, it turns out that if we want to reason probabilistically about models, most of the probabilistic inference queries that we are interested in answering are hard, are complete for this sharp P complexity class. So they are believed to be even harder than MP complete kind of decision problems like SAT or puzzles or integer programming. So what I will show you is that the following result, that even though counting problems are believed, inference problems are believed to be harder than MP complete problems, what we can show that is that if we allow some small failure probability, like the algorithm is allowed to fail maybe 1% of the times, and a small error, some small tolerance that we can choose and we can set any way we want, then we can reduce any kind of sharp P complete probabilistic inference query to a small number of MP complete, MP equivalent problems that are essentially some kind of combinatorial search or combinatorial optimization problem. And key to this result is that we are allowing some failure probability and we are allowing some small error. So the fact that we are introducing some kind of approximation allows us to reduce this, in a probabilistic sense, this inference problem to a problem that we understand better, where we simply have to figure out whether there is a way to set the variables in the problem such that some property holds, as opposed to the counting, the inference problem, where we're typically interested in queries like how many ways are there to set the variables in our problem such that some property holds. So now we're still taking a hard problem and we're reducing to another problem that we believe is hard. It's still MP complete. The good news is that in the past 20, 25, 30 years, we've seen a lot of progress in terms of combinatorial optimization and combinatorial search technology, especially in fields like satisfiability testing, mixed integer programming, for example. Solvers in the early 90s were able to handle very small problems with a few hundred variables, a few hundred constraints. Nowadays, we have industrial strength solvers that can handle very large problems with millions of variables, millions of constraints. And these techniques have found a lot of applications. I know some of you work in formal methods, so probably have used the SAT solvers, SMT solvers, integer linear programming solvers, especially in sort of deductive reasoning applications like verification, synthesis, or logistics, or scheduling, planning, these kind of problems. But by using this reduction, this probabilistic reduction that I'm going to describe next, we can actually use these techniques in a context of probabilistic inference, in the context of machine learning, in the context of inductive reasoning problems. So what is probabilistic inference? Well, the basic ingredient of a probabilistic inference problem, and I apologize for the very simple example, probably many of you are familiar with this, but just to make sure we are on the same page, the basic ingredient of a probabilistic inference problem is a probability distribution. So we have some random variables that I'm representing as circles here. They are binary. It can be either true or false. In this case, I have 3, representing whether the grass is wet or not, whether it's raining or not, the sprinkler is on or off. The probability distribution is a way to specify for each possible state of the world, for each possible assignment to all the variables in the problem, it specifies its probability or a weight that is proportional to the probability. And this, in machine learning and AI, is typically done using graphical models, so compact representations for this complex object that are based on the use of factor graphs or other types of graphical models, where basically the idea is that we can specify this complex object using a collection of factors, which effectively you can think of as weighted constraints that are capturing the dependencies over a subset of the variables. For example, they might say that whenever it's raining, it's more likely that the sprinkler is off than on, something like that. Then maybe we have a prior on the fact whether it's raining or not, and then we have other relationships. And the idea, the semantics of the model is that we get the probability for a full assignment of all the variables, like true, 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 by taking the product of the corresponding entries in the tables that specify the various factors. Okay. So what is the basic probabilistic inference problem? The basic problem that we care about is that of computing probabilities, making inferences based on the model. For example, we might want to compute what is the probability that the grass is wet. And by definition, what we need to do is we have to sum the joint over all the variables, which was specified by the graphical model, over all possible assignments of the random variable rain and sprinkler. So you see that computing expectations, computing probabilities, involve the computation of some kind of weighted sum, where we have to look at all possible scenarios, look at all possible assignments to the variables, and weight them with their probability. So this is the kind of problem we are interested in. A little bit more generally, we're going to assume that we have a very large state of possible worlds, say 2 to the n possible states of the world, corresponding to all possible assignments to n binary variables. Each one has a non-negative weight, which is specified. Think of using a factor graph, a Bayes net. Factor graph doesn't really, a weighted CNF, it doesn't really matter. And the goal will be that of computing the total weight of all possible states of the world. So we sum over all possible assignment, and there are 2 to the n of them of their respective weight. So in the previous example, we had 2 binary variables, the rain and the sprinkler. So there are 2 to the 2, 4 possible assignments. Each one has a non-negative weight, which was specified by that model. And the goal is to sum up these 4 numbers. So trivial. Of course, the challenge is if you have a more complex model, a more realistic model, a more interesting data set, you might have, say, 100 variables. Computing a probability will require will involve the computation of a sum with something like 2 to the 100 terms, and that's essentially, in the worst case at least, is believed to be intractable, and this is the kind of problem we're going to be interested in solving. Questions on the setup so far? Good. So let me describe how our approach works, and I'm going to do that looking at one example. Suppose we have a probabilistic model defined over 10 binary variables, x1 through x10. So there are 2 to the 10 possible assignments to these variables. I'm showing them here as a 1D plot, just to keep it simple. It's really a high-dimensional object, but I'm showing it like this, because that's the only way I know how to visualize it. Each one has a non-negative weight, and the goal is to essentially integrate this function. We want to compute the sum of the weights of all possible configurations. So we have 2 to the 10, 1,024 possible configurations. And to explain how the algorithm works, let me assume that I have them sorted by weight. We cannot really sort them because there are too many in general. This is just a visualization to explain how the algorithm works. So the goal here is to compute the sum of the weights of all possible configurations. And let's assume that we have access to an oracle that can find the weight of can find the configuration that has the largest weight. So it can find the mode of this distribution. And notice this is an NP equivalent type of combinatorial optimization problem that is believed to be easier than the problem of computing the sum of the weights of all configurations. So suppose we do that for this particular problem, and suppose that we get 50. So since these configurations are sorted, then we get a 50 on that tail of the distribution. Then what we can do is we can change the sign of all the weights or use a minimization oracle. And we can also get the weight of the least likely configuration, the one that has the smallest weight. And let's assume that in this case we get 0. So what do we know about all the other configurations? Well, we know that they are sorted by weight, so we know that their weight will be something in between 0 and 50, but that's all we know. So we can get a lower bound on the total weight. It's possible that they are all 0 except for the last one, which is 50, and in this case the total weight would be 50. Or they could all be 50 except for the first one, and in this case the total weight would be 1,023 times 50. So we can get a lower bound, we can get an upper bound, but you can see that they are exponentially far apart. So it's not good. In some sense it's nice because we've only used an optimization oracle, but it doesn't provide us much information about the shape of that distribution. So we're going to have to collect more information about this distribution of weights. And what we're going to do is we're going to find the weight of the second most likely configuration. And I will explain later how that's done. And you see that by getting more information, we can get better estimates about the lower bound on the total weight and the upper bound on the total weight. Because now we know that they must be between 0 and 40. Then we can get the weight of the fourth most likely configuration, the eighth most likely configuration. And you can see that as we get more information about this weighted distribution, this lower and this upper bound, they get closer to each other. And what I claim is that if you go all the way to the 2 to the n-1th most likely configuration, the 512th most likely configuration in this case, then this lower and this upper bound, they will get within a factor of 2 of each other. And this is remarkable because we have 2 to the n possible assignments, 2 to the n configurations, and we're only using n, essentially, reference points. So if you know the weights of these n reference points, then you have enough information to get a good approximation for the total weight. Yes?
Why do you not need all of them? If you need only less of them? I guess I missed something here.
So what I claim, so the intuition of why you can only get away with n of them. So you see that as the more you get, the better this lower bound and this upper bound get. And what I claim is that if you go all the way to the end, then this lower and this upper bound, they always get within a factor of 2 of each other. And the intuition is that we're collecting more points on this end of the distribution, where the heavy configurations are, and we can afford to be a little bit more loose on this tail of the distribution, because that's where the lighter configurations are. So the geometric nature here is important to guarantee that the error is sort of bounded. If you look at the plot, it's actually not hard to see it geometrically why this holds. It's like a simple upper bound on the curve and a simple lower bound, and you can see that they are with. This is not even a probabilistic statement. This holds in general as at this point. This is just essentially if you plot the curve, and it's just like a way to draw an upper bound and a lower bound that are guaranteed to be within a factor of 2, essentially. So this is nice. The question is, how do we get these quantiles of the distribution? How do we get the weight of the 2 to the i most likely configuration when I is large. So we know how to get the most likely, we know maybe how to get the second most likely, also the fourth, but how do you get the weight of the 2 to the 50th most likely configuration? You cannot just enumerate them. So we need to do something more clever here. And what we're going to use here, we're going to use parity constraints. So a parity constraint is just a linear equation modulo 2 over a set of, say, binary or Boolean variables. For example, A XOR B XOR C XOR D equals 1 is satisfied when an odd number of these variables are set to 1. This is the standard sort of logical XOR. So what we're going to do is we're going to start with our graphical model, our probabilistic model, or our original object that we want to do inference over. And we're going to generate a parity constraint randomly according to the following process. We're going to add each probability to the parity constraint with probability 1/2. So maybe we add x1, we don't add x2, we add x3, x4, x7, x10, and then we randomly pick a 0 or 1. We randomly pick a sign, and then we say that's how we generate the constraint. And then what we're going to say is we're going to say for every configuration, so for every assignment to all the variables, all in this case 2, 4, 6, 8 variables, if they violate this parity constraint, then we're going to set their weight to be 0. So pictorially, what happens is we're taking half all the configurations that violate the constraint, and we're going to set their weight to 0. So we get a new probability distribution that looks like this. And the nice property about this way of generating these random constraints is that they implement what's known as a strongly universal hash function, which means simply that it has the following two properties. First, every configuration will survive, so it will satisfy this randomly generated constraint with probability 1/2. So on average, we throw away half of the things. And the second one is that this process is pairwise independent. So given any two configurations, A and B, the events A survives and B survives are independent. And what this allows us is to show that by doing that, it will allow us to essentially get the nice accuracy guarantees are all relying on these two properties of the parity constraints. So how do we use them? Well, let's go back to the original problem. We wanted to compute these quantiles. Suppose we want to get the weight of the 64th most likely configuration, so 2 to the 6th. How do we do that? We start with our original model. We generate one parity constraint at random, then 2, 3, 4, 5, and 6, because 2 to the 6 is 64. What happens is that every one of them will roughly cut the space in half. We'll throw away half of the things. And so we're left with something much sparser that look like that. Then what we do is we use again our optimization oracle to find the mode of the most likely configuration that survives after adding these parity constraints. And what I claim is that the weight of the most likely configuration that we get after adding these parity constraints will be often close enough to the weight of the 64th most likely configuration, which is what we wanted to compute. And why does this work? Well, essentially there are two effects that take place at the same time. One is that we are using optimization, so we're trying to find the most likely assignment. And the other one is that we're throwing away a lot of stuff. So if you just use the optimization on this thing, we're going to get the mode of the distribution. But then because we're throwing away a lot of stuff using these parity constraints, it turns out that these two effects, they balance each other just the right amount, and you get the nice property that we want, that is this estimator, this quantity, will be close to what we wanted to compute more than half the time, and so you can sort of amplify it to a result that holds with high probability. So this is the basic idea. This is how the algorithm works. This is, again, a visual representation. We start with our original model and binary variables, 2 to the n possible configurations. Each one has a non-negative weight. What we do is we initialize by finding the mode of this distribution, the most likely state. Then we randomly generate one parity constraint, throw away half of the configurations, find the mode of what's left. We repeat this process roughly log n times. Here n is the number of variables, generating different constraints every time and finding the mode. And then we compute the median of the results of these optimization problems. Then we do the same thing with 2 parity constraints, randomly generated. Again, cut the space, only we're roughly left with 1/4 of the configurations every time. Repeat it, and we do this all the way up to n parity constraints, so n times. And then how do we get our final estimator? Well, remember that these medians are going to be our estimators for those quantiles that were geometrically far apart. They were spaced with these powers of 2. So all we need to do is we just have to weight them geometrically because they were geometrically spaced. And this will be our final estimator for the total weight, so for the integral for the area under this curve. Yep.
Why do you compute the median?
The median is just to get a high probability result. So effectively what happens is that what I said here, this result holds, say, more than half the times. So if you take a median, it will hold, say, with probability 99% or whatever number you want. You just need to, it will, because they are all independent, so you get Chernoff bounds, it converges really quickly to what you want. So it's to get a high probability. Yes. Yeah. So this is the final result, informally stated, with probability at least 1 minus delta for any desired delta, so maybe 99.9%. This algorithm will compute the sum over 2 to the n configurations with a relative error that you can make as small as desired. The algorithm I showed will give you something like a factor 16 approximation, but you can make it as small as you want. And it requires solving something like n log n optimization instances, because remember, we're doing log n and n times. So as promised, we can take an inference problem, a counting problem, and we can reduce it to a polynomial, a pretty small number of optimization problems with guarantees. So it's nice because it has good accuracy guarantees. You can leverage all those nice solvers that are out there for solving combinatorial optimization problems. It doesn't make any assumption on how you solve these problems. Even when you cannot solve them to optimality, say you can get lower bounds because you do local search, or you get upper bounds because you take some tractable relaxation from an LP relaxation or an SDP relaxation or something. These bounds translate automatically into upper and lower bounds on the counting problem. And it's straightforward to parallelize. You can solve each optimization problem independently, so you can just ship them to different cores and parallelize it very nicely. Yeah.
Your method right now, like on previous slide, says that you need to run at least n parity constraints. So if n grows really, really large, then you cannot possibly go through all parity constraints. So is there some guarantee that you can run it for high dimensional spaces that you don't have to run as many constraints and still get a good estimate?
So, well, you're worried about the length of the constraints or the number?
It doesn't matter, but the number of times you have to keep repeatedly.
Well, but and if n maybe 1,000 or something like that, that's not too bad. Like you're adding 1,000 or maybe 900 constraints or something like that.
But
so it does make the question is how much harder does the problem get after you add parity constraints?
Millions, then you will run into some.
Yes. But I mean, we're starting with some very hard problem. We're trying to integrate a function over 2 to the n possible assignments. So. But yeah, you're right that the key question is how much harder does the problem get after you add parity constraints, and we're going to talk about it later. Yeah.
So these for computing the integral of that function. Can you use the same technique for computing other statistics that we might be interested in?
Yes, as long as it's the only assumption that we made was basically that it has to be non-negative, and so it's an integral of something that is non-negative. So how does this work in practice? Let me start with a simple example just to show you what's the idea here. You're probably all familiar with Sudoku. You have this puzzle. The goal is to fill it with numbers so that you don't have the same number twice in the same row, column, or subsquare. You can view the problem of filling a Sudoku square as a combinatorial search problem. It's very easy to solve with, say, a SAT solver or a constraint satisfaction problem solver. Now you can look at the problem of, what if I ask you the following question? How many different ways are there to fill a valid Sudoku square? Well, this is one, this is another. How many are there? And we can view this in the framework that we just talked about. We are trying to sum over all possible squares, and there are a lot of them. And we want to weight each one of them 1 if it's valid and 0 otherwise. So it fits into this framework that we just talked about. And so we can use the technique that I just described, and we can use, say, something like a SAT solver. We can reduce the problem of counting how many valid Sudoku squares there are to the problem of filling Sudoku squares subject to parity constraints. And it turns out that by running the algorithm, you get a pretty good estimate here, which turns out to be close to ground truth that was actually computed with some specialized proof by some mathematicians. By using some symmetry properties, they were actually able to work out the actual number. And you can see here that it gives roughly the right number here.
How do you get 10 power 77 squared?
I think I just checked all possible ways to, there are like,
Shouldn't it be 10 power 81?
I,
Some squares are full. Some squares are already.
yeah. So more interesting benchmark sizing models here. They are models from physics. They're also used in vision. We have binary variables. They interact with each other. Some of the connections are strong. Some of them are weak. And the goal here is typically to compute the partition function for these models, which is just the sum of the weights of all possible assignments to the variables. Here are some results as a function of the number of variables, the normalization cost that you get using Wish and some other competing techniques. And we can get ground truth, which is this green triangle, up to about 25, 30 variables. That's as far as you can go by doing brute force enumeration. You can see that we can get Wish to work up to about 60, 65 variables. And there is a tiny error bar around each point, which is the guarantee that we get from the theorem. We know that the ground truth is going to be within that error bar with high probability. And you can see that for large instances, the kind of solutions that you get using competing techniques, although we don't know where exactly ground truth is, we know that it's within this error bar, and so they can be off by several hundreds of orders of magnitude. Similar things for computing marginal probabilities. Here I'm showing a scatter plot of the sort of the probability that each variable is true or false, the estimated one versus the true one. You want to be on the diagonal here. And if you run Gibbs sampling, you can get very inaccurate results because sometimes it takes a very long time for the Markov chain to mix, to reach the stationary distribution. Running Belief propagation, also very inaccurate results. Using this technique, you can get much more accurate estimates. This is by running it for exactly the same amount of time. So it's not, this is really a fair comparison, like the same amount of CPU time, you can actually get better results by using this technique. So before, it was a click. So in that sense, it was really hard. These ones are just the grids with sort of frustrated potentials so that Gibbs doesn't mix. Yeah.
So when does it not perform better?
Well,
Does it ever not perform better?
it doesn't when you cannot solve the optimization problems. Or there are cases where Gibbs will just work, it will converge really quickly. And this will take forever because it's trying to find you, essentially it provides you a certificate that what you get is the answer that you're looking for. So typically what happens is that it will probably give you the right answer very quickly, but then the solver will take forever to prove that that is indeed the answer that you're looking for. And if Gibbs happen to be giving you the right answer, then you're just wasting your time, and then the comparison is not really fair. But indeed, there are problems where this takes forever, and that you cannot really solve. Yeah, and I think actually a very interesting idea would be how do you figure out, given the result that you get from a Gibbs sample, can you use these kind of techniques to provide a certificate, like to validate and give you a proof that indeed the chain has converged, or that you can trust the results that you get. because we typically don't have a good way to do it. We have heuristics, autocorrelations, and whatever, but nothing is sound, is conclusive, right? So it will be very interesting to see if there is a way to do that. So now I want to talk a little bit about a different view of these hash functions. Remember, we were using these hash functions to essentially split the space into half and randomly throw away half of the space. And one way to think about this process is as a distributed coin flipping mechanism, where we have a bunch of configurations, all possible assignments to the variables. And one way to think about what we're doing is we are essentially trying to make each configuration flip a coin. And based on the result of the coin, it ends in one of the two hash bins, the heads or the tails. And so ideally, we would like each configuration to flip a coin, divide it to all the possible configurations into two hash bins, heads and tails, then throw away half of it, then throw away one of the two bins. This is essentially what we're trying to do with these hash functions. The challenge is that if we are asking each configuration to flip a coin independently, this is going to be very hard because it requires too much randomness. There are 2 to the n possible configurations. There is no way we can do this. It will just require too many bits, too many random bits to be able to simulate this kind of approach. So our solution was, well, we showed that actually you don't really need all these coin flips to be fully independent. It's enough that these coin flips are pairwise independent. So if you look at any pair of them, they are going to be independent, but if you look at 3 or more of them, there could be some dependencies. And this is something that works in the sense that it gives you good enough statistical guarantees so that you can prove that the results that you get are going to be accurate with high probability. And importantly, you can simulate these you can essentially store them in a compact form using these parity constraints. So if you add each variable probability 1/2, it's like simulating 2 to the n pairwise independent coin flips, where each coin flip is essentially, does this configuration satisfy the random parity constraint that I just generated according to this strategy? So we're giving away some of the independence, some of the statistical properties of these coin flips, but it's something that we can essentially encode in a compact way, because we just need essentially n bits to generate, n random bits to generate the parity constraints, and that's enough to achieve this result. Now, is pairwise independence really needed? And is it possible to actually use parity constraints that are shorter? Like the constraints that we generate using this process will have, on average, a length of n/2, because we add each variable with probability 1/2. And as you were mentioning, it might be hard to solve optimization problems subject to parity constraints that involve a lot of variables. So it would be nice if we can come up with a way to generate shorter parity constraints and maybe give up a little bit of the statistical properties of the coin flips that we generate. And so this is something that we came up with a couple of years ago. It's a new class of hash functions that we call average universal. And if you think of them as coin flips, essentially what this class of hash functions does is the following. It's weaker than pairwise independent in the sense that there are pairs of coin flips that are far from pairwise independent. But if you look at large enough sets of coin flips, and then you look at all possible pairs of coin flips in this set, then on average, they are going to be independent enough that the proof follows through. And the main result is that if you are careful and if you specify these constants and this number correctly, these coin flips are going to be good enough to give you exactly the same theoretical guarantees from what we had before. And it turns out they can be implemented. You can generate them using sparse, short parity constraints. So you don't have to add each variable with probability 1/2. You can add each variable with a smaller probability. And we actually proved recently that a necessary and sufficient condition on the length of the parity constraints that you need in order to get good statistical properties. So we actually showed that parity constraints of length roughly log n, at least asymptotically, are both necessary and sufficient to get the statistical properties we discussed. And this is nice because a parity constraint of log nth can be encoded with a polynomial number of, say, clauses in CNF. It gives you the same, and it gives you the same theoretical guarantees as before, and they are much easier to solve. And we also, as part of this proof, we actually worked out some theoretical results that hold no matter how short or long the parity constraints that you use are. So for example, you can even use parity constraints of length 1, where you're fixing a variable to take a particular value, and that will still give you something that you, will give you some pretty bad statistical properties for the coin flips, but you can still work out, you're still able to say something about the total weight of the configuration, about the original probabilistic inference problem that we wanted to solve. And the proof here, it uses some ideas from the theory of low-density parity check codes. It turns out that, not surprisingly, we are trying to generate these random matrices and that essentially correspond to linear equations modulo 2. And that's something that has been studied a lot in information theory to understand the properties of these error-correcting codes. There is a one-to-one correspondence between error-correcting codes and hash functions, where essentially the statistical properties, like the clash probability of the hash function, maps to the information theoretic properties of the code, like the average distance between code words. So this result is not entirely surprising, but it follows nicely. And in practice, the short constraints are much, much, much easier to deal with in practice. So here, for example, we looked at some model selection problem in machine learning, where you have several competing statistical models for some data. The goal is to figure out which one is most likely to have generated the data. The problem is that in a lot of models of interest, the probabilities are defined up to that normalization constant, that partition function. So if you want to rank several candidate models, you're going to need that partition function that we can compute using the technique that I just described. So here we looked at RBM models, Boltzmann machines. It's like the building block for deep generative models. And we looked at several models that were trained using different learning algorithms. And the goal is to see which one looks better, which one is more likely to have generated data that looks like this, which are actually handwritten digits by some persons. And it turns out that using short constraints and some of these ideas that we just described, we can scale to very large problems, and we can get state-of-the-art estimates on the partition function of these restricted Boltzmann machines. So we can get the same accuracies as, say, annealed importance sampling. We get some nice guarantees on top of that, and we are using completely like a black box technique. We're just using optimization plus parity constraints. We're not engineering any proposal distribution or anything. So to conclude, I want to give you another view of these random parity constraints. This view of random parity constraints as random projections. Remember, we have these parity constraints, and the way we use them is we start with our original probabilistic model. We generate a parity constraint by adding each variable probability 1/2, and then we set the weight to 0 for all configurations that violate this parity constraint. And you can view this operation as a random projection on the space of probability distributions. So it's random because we are generating the constraints randomly. It's a projection because if you add the same constraint twice, it's not going to have the same effect as adding it once. So in that sense, is it important? Like if you apply it twice, you get the same thing as applying it only once. And it behaves, this kind of random projection has some nice properties. The first one is that, in some sense, it simplifies the model because it throws away half of the possible configurations. One way to think about it is that it reduces the degrees of freedom by 1 because it's adding this kind of constraint. So by adding one constraint, you're reducing 1 degree of freedom. The model becomes simpler. And because of these pairwise independence properties, because of these good statistical properties of the coin flips that we use, it can be shown that essentially, with high probability, this projected model has an preserves some of the key properties of this original model. In particular, the total weight of this model is going to be half the total weight of this guy with high probability. And so the natural question here is there a way to use this other ways to use these random projections? One recent work that we did is we were able to use random projections in combination with variational methods. So very crash course on variational inference. The basic idea is that it's an inference method that came from statistical physics, also widely used in machine learning and AI. The idea is that we have an intractable probability distribution, a model P, that we want to do inference with. It's intractable, so what we do is we consider a family of simple tractable distributions that we call Q. And then what we do is we try to find the simple distribution, this as close as possible to P, based on some notion of distance, on some notion of divergence. And that's called an I projection, an information projection. And so that's this is pictorially, this is the point, the tractable distribution, and this is as close as possible to P based on some metric, which is KL divergence in this case. The challenge is that there is no way in which you can bound this distance between P and its approximation. This is the key issue with all variational techniques. Essentially, the approximation can be arbitrarily bad, and the reason is that P could be too complex with respect to this family of distributions. If P is really complex, Q is too simple, you cannot approximate well, no matter how well you even if you find the closest point, it might still be very far. So the idea here is what happens if we take a random projection of P? Well, we know that in some sense the properties of P are preserved, because we're using this pairwise independence, these parity constraints. And P prime, what we get by doing this random projection, is going to be simpler, is going to have less degrees of freedom. And we can show that it's actually guaranteed to be close to Q, because we're simplifying it. So the natural idea is to do first a random projection, and then take an I projection of P prime. Because we are guaranteed that P prime is going to be close to Q, no matter how complex your original model was, by taking random projections. And what this does is that you can prove that what you get by doing this, by essentially approximating P prime and then backing, since P and P prime essentially have P prime has all the information you need about P. If you can approximate P prime, you can approximate P essentially. And so what you get is that you can get a provably good approximation with high probability. Assuming you can solve this optimization problem, you can find the closest point to P prime, this will give you a provably good bound like the one we had before for the original wish technique. Q is a family of tractable distribution. Think about mean field, something simple that you can do inference with. Almost. It has to contain Dirac deltas, like essentially all the Dirac deltas. So it's fairly mild restriction. Mean field would work. Anything more complex than mean field would work. And I think, well, mean field is probably the simplest you can think of, so pretty much anything would work. Yeah.
So again, when would this method fail if the random projection is not really decreasing the distance?
They will always do. That's guaranteed.
But then why is it with high probability, not with probability?
Oh, because you just have to repeat it a bunch. That's not an issue. Like that, you just repeat more times and take a median, and you can get to 99.9999 whatever you want. So that part is not an issue. The real challenge is that you need to be able to compute this I projection, and that's generally hard. So even computing this I projection is not easy. It's a non-convex optimization problem, so you might not be able to do that. So that's sort of the no free lunch part. Assuming you can do a good job of finding variational approximations, it's better to take a random projection because you get probably good results. But that's still a non-convex problem, so you might not be able to do it. And actually, what you get if you take the random projection, essentially you get the same kind of optimization problem. So the same objective function, you get less variables because you essentially remove some degrees of freedom by taking these parity constraints, but you have additional non-convex constraints in the optimization problem. So those might make your life harder. The good news is that it's still coordinate-wise convex, like traditional sort of variational inference stuff. So you can still look for local optima reasonably efficiently just by optimizing one coordinate at a time. Yeah?
So you don't actually solve the eye projection?
I do. Yeah, we do. Yeah. We take first a random projection and then an eye projection. And we do it by just taking the standard sort of approach of taking coordinate ascent on the variational lower bound. It's still coordinate-wise convex, so you can still use the same algorithm essentially. So, but you might get stuck in a local optimum. So you don't, in that sense, you don't have proof because it's a non-convex problem, so you don't have guarantee. Yeah. You're literally finding. You might not be able to find this point. Maybe you find something here or here, because you're not solving the problem to optimality. You might get stuck in a local optimum. That's the issue. And it works well. These against our RBMs. Here you can see the difference between taking an eye projection, just do mean field variational inference. Here, this picture should look like an average of all possible digits, so it should sort of look like an 8. And if you don't take the eye projection first, you can get some really bad sort of marginals that don't look at all like digits. But if you augment it with random projections, you can get better approximations of the probability distribution that you were looking for. So, yeah, I think that was it. The summary is we have this new approach to do probabilistic inference that complements MCMC and variational techniques. The key idea is to use universal hashing and some form of optimization. We've seen you can view hashing as a distributed coin flipping strategy. I think that view, you can think of it as a randomness amplification approach. That's a useful view to think about what it's actually doing. Another way to think about it is as a form of random projection that is simplifying the model while preserving some of the key properties. And we can leverage existing combinatorial solvers and SAT solvers, SMT solvers. We've used all these within this technique. It's nice because it provides formal accuracy guarantees. So if you have a SAT solver or an integer linear programming solver, something that gives you a formal certificate that you have an optimal solution for your optimization problem, then you have a certificate of accuracy for your original probabilistic inference problem. And it seems to work well in a number of real-world domains. But there is more to do, more to explore. And yeah, this is it. This is the high-level idea. Is we have these big challenges, high-dimensional spaces, uncertainty. They need to optimize for objective functions and utility functions. And I think there are great opportunities for combining ideas from the deductive reasoning world, like constraint satisfaction, theorem provers, with the inductive reasoning world, the machine learning idea, probabilistic inference, the idea of taking data, extracting knowledge. I think there are great opportunities for closing the loop here, using these ideas to get guarantees in the machine learning world. At the same time, there are interesting opportunities for using these kind of techniques to speed up combinatorial optimization solvers, constraint satisfaction solvers, and things like that. And I haven't had time to talk about all the applications, but we have a lot of them. I think they're pretty interesting, especially in the physical sciences. There is often a lot of prior knowledge about the domains, like physical laws. We have some work with material scientists where we're building these models where we use data. And some approximations of the laws of physics about the domain that they care about. And we're using SMT solvers to jointly reason about the data and the physics and try to understand the crystal structure of the materials they generate. And so I think it's pretty exciting, and hopefully we're going to see more of this in the future. And this I think is the natural next step for AI, is really to take these great advances that we have seen in machine learning and combine them with more formal reasoning techniques and really take it to the next step. And that's it. Thank you.